So is G the inverse of A, of F? I'm a bit fuzzy on that one. I need to clear that up in my own mind a bit. Anyway, so if you're now starting to think of these bijective mappings to the same set, think of them as now elements in a group. Okay? So we're suspicious now that the set of bijective mappings between the same set, so between A and A, okay? So these F and G and in fact all bijective mappings from A to A, so all of these F's, right? That's your set. The binary operator is just followed by. So you're doing things like F followed by G. Okay. Now F and G are bijective. If G is bijective, where did we prove that? In the text, it just follows immediately from theorem 33, which is just here. So okay, right. So FGGF are bijective. Okay, so therefore you've got closure. Okay, so if you know your binary operation is just to make a composite function. The set is the set of all bijective mappings between the same set, between A and A. Okay, so there's your set. Your binary operator is just to just perform one operation, one mapping after the other, one function after the other. So create a composite function. That's your binary operator. So the result of this binary operation, FG, is also bijective. Therefore, it belongs to this set. Okay, closure. Okay, you've got closure. Associativity we've got for any three of these bijective mappings from A to A. Associativity is true in general for mappings. So you've got closure, associativity. You've got the unit. That was the identity functions. These, right? Each. Now we're only talking A, so we don't have C. We only have like A, right? So we have a unique identity. So we have an identity, and what's the other thing we're missing? And the inverses, right? If F is bijective, there's an inverse. Right? If G is bijective, there's an inverse. So for each bijective function, there's an inverse. So we now have all four possibilities. So the group that I was hoping that you would find, if you're thinking ahead, is this. So the group is the set of all bijective functions between the A and A, the same set. Binary operator is just form the composite function. You just perform one operator followed by the other. Okay? And all four conditions for a group are satisfied. Therefore, this set of all bijective operations, so one-to-one operations between A and A, that is a group. And I'll close by saying, if this set A is finite, let's say the size of this set is M. Let's say there are M elements in this set. Then how large is this set of functions? How many bijective operations are there between A and A? Now bijective, remember, is one-to-one. Okay. So imagine you've got like m points, m elements here. And that's 1 to 1, so they map 1 to 1. Well look, the first one could map to the first one, but it could map to the second one, or it could map to the third one. So you'll have m ways this first element could map. Okay? So that leaves m minus 1 possibilities for the second one to map, because one place is already taken. You can't map two different elements to the same, right? It's 1 to 1. It's bijective. Okay. So once you've mapped the first one, that leaves m minus 1 possibilities for mapping the second one. So how many ways can you map the first two elements of your A, of your domain? Well, it'll be m minus 1. Okay? Now if you've done any combinatorics, permutations and combinations, you're probably familiar with this from high school maybe. Okay, now what about the third one? Now already two already taken, so the third one will have m minus 2 possibilities. So how many ways can you map all three? Well, it'll be m times m minus 1 times m minus 2, and so on. And it takes you all the way down to 3, 2, and when there's only one left to map, all the others are mapped, there's only one unmapped member in your codomain, so you can do that in only one way. But that, by definition, is m factorial. Right? M factorial means m times m minus 1 times m minus 2, 3, 2, 1. Okay? So this set here, or this group here, its size, now we're talking group, therefore its order, so the order of this group is therefore m factorial. Okay? And, well, there's a lot of theory on this kind of group. It has a technical word. It tends to be called, well, it's a kind of permutation group if you think about it. And in fact, a whole lecture, a couple of lectures from now, will be on permutation groups. But this type of group in general, I mean, it doesn't have to be about functions, but when the order, when you're permuting in a sense, this group tends to be called a symmetric group of order m, where m here is the size of your group, or its order, the order of a group, number of elements it has. Okay? Well, that's the end of this lecture, a long one. It's getting harder, right? More and more proofs. Now, the next lecture will be on the concept of isomorphism. Iso means same, morphism means shape, so the same shape. So if you have two groups, same size of course, if they're not the same size, isomorphism is just completely out the window. But if you have two groups the same size, same number of elements each, and if you can show, now you might have to translate the symbols of the elements of one group into the equivalent symbols of the elements of the second group. You might have to translate one set of symbols into another set of symbols, and you may have to rotate columns and rotate rows in the group table. But if you do that, if you translate and you're shifting around columns and rows in the group table, if your two group tables end up being identical, then those two groups, even though their sets may be totally disconnected, like one might be about numbers and the other one might be about rotations or whatever, so completely different set, and the operations have no connection at all, but their group table, with translation and flipping around and whatnot, rows swapping around, columns swapping around. If you can get those two tables, group tables, to be identical, then those two groups corresponding to those two tables are said to be isomorphic. And when groups are isomorphic, superficially they may have nothing to do with each other, you think. But if their group tables are the same, they are effectively the same group. Right? Isomorphic groups are, in group theory terms, they're the same. They're just the same group. Now remember, the operations of a group, it's very abstract, right? It's like extracting what is this group having, what does this set with its binary operator have in common with this one or that one. So if they all have identical group tables, and remember the group table has the total information about the group. If you have the group table, you know everything there is to know about that group, because it's all there in the table. You can find its inverse, you can show that it's associative, you can prove, you can find the inverses that it's associative, that it's closed, and that there's a unit. Right? So you can, from the table, you can deduce those 4 properties and then hence show that it's a group. So that's, you know everything. Okay, so I'll stop there, and I say, we're halfway through now. I'd say we have definitely left the junior level behind. It's getting harder. We're now well into senior level territory, and as the lectures unfold, there'll be more and more proofs, and they'll get a little harder. Like today's was not trivial, seven proofs, and took a while. So that's the pattern to be expected. So brace yourselves. So see you next time. Ciao.